Hi, in this video, let's look at some examples where we have been given graphs of functions, and from the graphs we compute right-hand limit, left-hand limit, and also the two-sided limits if any of them exist. So let's look at this graph first. I have a number A marked on the x-axis and I have a number L marked on the y-axis, and here's my graph. Notice right away that f of A is undefined. That's what this unfilled circle is telling us. And here we would argue that limit of the function as x approaches A from the left-hand side and also the limit of the function as x approaches A from the right-hand side is exactly same as L. To convince yourself of this, look at the picture. Look at a point to the left of L. That's what this negative is telling you. Very close to L, but never at L. Go up to the graph and read out the y-coordinate of the point. It is close to L. You can see that as you get closer and closer to A from the left, but never actually being on A, the corresponding y-coordinate values of the points get closer and closer to L. That's how we can figure that this left-hand limit is L. Similar argument for this. Since both the left-hand limit and right-hand limit exist and they're equal to the same value, by our definition of the two-sided limit, this two-sided limit exists and it is equal to this exact common value. In fact, these three statements are true for this graph also, which is exactly same as this. The only difference is this time I added in this extra point. That means f of A is defined, but notice f of A is not same as L, because what is f of A? We would look at the point and then go up to the y-axis, and whatever that value is, that would be f of A. It's not equal to L. But these answers do not change, because to compute left-hand limit or the right-hand limit, or in fact the two-sided limit, we never look at what the functional value is at A itself. X is never A when x approaches the point A. So that's why these answers are the same for this graph too. And for this graph, this is very similar to these, except this time f of A is defined, and furthermore f of A, I arranged it so that it's exactly equal to the value of L. Even so, all these answers remain the same for the reasons I explained before. It might occur to you somehow that this example 3 is a little bit different from 1 and 2, because in this case f of A is defined and it is equal to the two-sided limit, and you're correct. So when the left-hand limit equals the right-hand limit, and thus the two-sided limit exists and is equal to L, and furthermore if the function is defined at that point A and f of A is equal to L, that is a very special case. In another video, when we discuss continuous functions and the concept of continuity, we'll come back to this example. For now, try to understand why for 1, 2, and 3 these answers remain same. Now let's look at a different category of examples. Let's discuss one example carefully, and you'll see why I put all these 4 pictures on the same board. So on this example, notice that f of A is undefined, and let us try to compute the left-hand limit for this function. So I approach A from the left-hand side. So that means you might as well not look at this piece of the graph. So x approaches A from the left-hand side, so I look at points very close to A but never being on top of A. and then I go up to the graph and then go up to the left and read off those functional values. As you can see, they're very close to L. And as you get closer and closer to L, notice if you go up to the graph and then go left to the y-axis, those y values get closer and closer to L. So that's how we get that the limit of the function as x approaches a from the left hand side is equal to L, this value of L. Similar argument you can do to find the limit of the function as x approaches a from the right hand side. Look at this picture and begin to look at points on the x-axis that are very close to a. Go up to the graph and go up to the left and read off the y coordinate of those points. You'll notice they're close to the number r. The closer you are to a, but never being at a itself, you will notice if you go up the graph and go to the left, then that y value is very close to r. That's what you will find. The fact that f of a is undefined is irrelevant when you compute left-hand limit and right-hand limit, because of the way we have defined left-hand limit, right-hand limit. Also, by the definition of two-sided limit, we say it exists only when the left-hand limit and right-hand limit are equal and it equals the common value. Here's a situation where the left-hand limit and right-hand limit are two different numbers, two different points on this number line. So in this case, the conclusion is the two-sided limit does not exist. DNE is a shorthand notation for does not exist. And the reason is since L is not equal to R. That same argument works for each of these graphs, which you can go through carefully. Here I have added this extra point to the graph. That means f of a is defined. But like I said, when we compute our left-hand limit or right-hand limit or two-handed limit, we are never concerned with f of a, f of that point. And here, again, they're very similar to this, except I have added an extra point here. So in this case too, f of a is defined and f of a is equal to L. Here f of a is defined and f of a equals R. But that piece of information is completely irrelevant to make these computations. So when you study this topic, see why I put all these four on the same board, because they're really very similar and the answers are all exactly the same. They only differ in what happens at f of a, and f of a is irrelevant when we compute this. So the first set of examples we looked at were the kind where the left-hand limit, right-hand limit existed and they were exactly equal. So this is our second set of example where both the left-hand limit, right-hand limit exist. They are finite real numbers, but they are different finite real numbers. Now let's look at examples where one of the limits does not exist. Here's another set of examples. Look at this, and together and compare them. So let's look at this graph. Convince yourself that the left-hand limit exists and is L, because if we approach A from the left, that means we're looking at a point very close to A, on the left of A, never at A. Go up to the graph, go to a point, and then look at the y-coordinate of that point by going to the left and reading off on the y-axis. That's a number close to L. As you get closer and closer to A, but never being on top of A, you'll see that corresponding value gets closer and closer to L. That's how we figure out that the left-hand limit is L. Now what happens to the right-hand limit? It does not exist for this reason. Look at this. As you get closer to A, look at the functional value of that point. Go up to the graph, find a point, and the y-coordinate of the point you can read off by going straight across to the y-axis and whatever that number is. It is clearly greater than L. the closer you get to A, you can see the functional value of that point keeps getting bigger and bigger and bigger, and it is not going to approach a finite real number. So, which is why we say that the right-hand limit does not exist. So, the minute one of the limits does not exist, then clearly the two-sided limit does not exist. The two-sided limit exists only when the left-hand limit exists, right-hand limit exists, and they are both equal to the same value. In this case, the right-hand limit doesn't exist, so that means the two-sided limit cannot exist either. This graph is only slightly different from this in that I have added that extra point to the graph. That means f of a is defined, but as I said before, the value of f of a does not affect these computations. So that extra information does not change your answers. Same argument here. I've added this point here. So in fact, f of a is L, but that piece of information does not change these answers. Now let's look at this example where neither the left-hand limit nor the right-hand limit exists. And I will leave it to you to convince yourself that these are true for this graph. And now this is our final example, an interesting or a bizarre example, however way you want to look at it. Here's the function f of x equals sine of 1 over x. You can use your favorite technology to graph it. This is not a great picture, but I'm sure if you use technology, you'll get a better picture of it. So let's look at this graph. What do you notice? The functional values are always between -1 and 1. This is because of this sign. And you will notice this kind of oscillations. And I'm interested in limit of f of x as x approaches 0 from the left and also from the right. Do those limits exist? And the answer is no. Neither one of those limits exist, exactly like this situation, and hence the two-sided limit doesn't exist either. But let's discuss in detail, because the reason why these limits do not exist for this example are very different from the reasons why these two limits do not exist. So looking at it, recall the reason the left-hand limit doesn't exist for this example is because as we approach A from the left, you'll notice from the graph that the functional values keep getting bigger and bigger and bigger. Here, that is not the case. So let's look at this. As we approach 0 from the left-hand side, notice because this function is always between -1 and 1, the functional values never get larger, but instead what happens from your graph that you've drawn using technology, notice that even if you get very, very close to 0 from the left, these oscillations continue on infinitely. So even if you're close to 0, within that space, these oscillations continue on, always between -1 and 1. That means if you approach 0 from the left, you'll notice the functional values do not settle down on any number that we can call as L. In fact, no matter how close you get to 0 from the left, within that small interval, you can find points such that the f of that point is any number between -1 and 1. So, it is for that reason that the left-hand limit doesn't exist, and similar reason the right-hand limit doesn't exist. So compare this graph with this graph. In each case, neither the left-hand limit nor the right-hand limit exists, but the reason is different. So in the next video, we will once again look at right-hand limit, left-hand limit, and also the two-sided limit. And we will compute it using numerical methods. So we'll still keep everything on an intuitive level. At that time, we'll revisit this function. Thank you.